All right. Hi, everyone. Welcome to our webinar today, The State of the Art of CFD, Computational Fluid Dynamics in the Water Industry, a decade of international case examples. So I'm Wim Oudenaert. I'm very excited to be the host today, to be welcoming you in this webinar. We have really plenty of people signed up, over 200 people signed up for this webinar from different time zones, different continents across the globe. So we have quite an international audience here and a very good mixture of people working on technology, people working on operations, and people working on engineering and design. Yeah, very excited to be witnessing the discussion today, and we hope to provide you lots of value. CFD is something that is really in the core of our business, AM team. Still today, we are very, very well known for this. We work with customers all over the world. We are very specialized in this area, even though we also do digitalization and digital twin applications a lot. CFD has been always an integral part of our business. So we are very, very happy to give kind of this milestone webinar to you where we summarize and make kind of an analysis of all of these years of cases. So let's look at the content of today, the objectives and the format. So what is the context? Well, we are in a very interesting industry. We are working in a very important industry. And lately, let's say the last couple of years, the last decade and the coming decades, our industry is really facing unprecedented challenges. So the challenges come way faster than ever. The decisions have to be taken way faster than ever. And design has become quite a complex and a balancing act. And I'm talking about wastewater, drinking water, reuse, all of these areas. And this makes this webinar today very relevant. So the objectives of today are that you have a very good understanding of the capabilities of today's CFD models and simulation solutions. So this is really what we hope to provide. And also that you are a bit inspired by the wide array of applications across our industry. There are really many. We will not be able to cover all of those today, but we hope to give you a very good overview of all of it. So this is really our aim, to give you a very wide overview so you don't have difficulties understanding where to apply it and where it can really serve as a very good business case. So we will have a huge variety on drinking water, wastewater cases, reuse, you name it. But even though you're not working on a specific domain, we will be showing in a specific case, we think the cases will be relevant for everybody because you can look at it conceptually for sure. The hybrid, we will have a hybrid format, some presentations, some live questions and answers. We will have a discussion. And please use the Q&A. If you hover over the screen, you will see a Q&A button. Please use the Q&A window to ask your questions. We will be flagging them. We will be bringing them live if they are relevant to the wide audience. So don't use the chat. We will also have some intermediate polls to probe what are your thoughts. And after the webinar, there will be a short questionnaire that will pop up. So please fill this in. This is very important to us. So before we dig into the content, I want to make some publicity online for our huge amount of webinars and movie material or blog posts online. You can visit our YouTube channel, and there you will find every single webinar we have done in the past on specific topics. So this webinar is very broad. It is on the general topic of CFD, and we will handle several applications. But we have webinars specifically on greenhouse gas emission reduction, on biological wastewater treatment process optimization, on micropollutant removal, advanced treatment, all of these things together. So you can really visit there to really dig into the content. So again, this is a wide overview webinar where we will not dig into one specific topic very deeply. This is not the purpose of today. So this is the webinar team. I'm Wim Oudenaert. I'm CEO and co-founder at AM Team. And then we have Roberta. So Roberta is joining from Italy. She is project manager and senior simulation engineer. She has worked on numerous amount of cases across the world for many, many customers. Then we have also Usman joining. Usman is my fellow co-founder and CTO of the company. Usman will be monitoring the Q&A, the questions and answer, and participate in the discussion. Then we have Peter Vlasgaard. So he's our VP Sales and Solutions. Many of our customers will know Peter because he sets up all of these projects, all of these big projects with them. We have Simon as well. Also, many of the customers will know him because he also works on a lot of projects as a project manager and a senior simulation engineer. And then we have also Constanza. Constanza has been setting up the webinar behind the scenes and has been interacting with a lot of our customers. So she is solution engineer in our company. So on behalf of our whole team, I am welcoming you to this webinar. So before I give the floor to my colleagues, we will start with a poll, and I will first probe a little bit in which stages you are involved in. Are you involved in technology development and commercialization? Are you involved in planning and design, or more at the operational side? Are you really operating plants? So feel free to vote. You can also vote multiple times because some people are involved in multiple of these domains. So the votes are coming in. We are almost having 100 votes now. They're adding up. So I will give it 3 more seconds, and then you will see the results as well. I think it's interesting to see for you as well who is in the audience. So I will end the poll now and share the results with you. So the most of you, so like more than half, let's say, are involved in design, which makes a lot of sense. CFD is really a good design tool, but many of you are also involved in planning, a significant fraction in technology development, so at the technology end, and quite a bit of you in operations as well. Why? Of course, we have quite a couple of utilities today attending as well. So that's interesting. Thank you for sharing your thoughts. So I will now hand the floor over to my colleague, Peter. Peter will be introducing CFD in an understandable manner, let's say, and the specific application in the water industry. So Peter, the floor is yours.
Yes, thank you, Wim. So indeed, I will explain you a little bit more about what CFD is and what it can do for the water industry. But let's maybe first go to some history, where it all started with CFD. So actually already in the 80s and in the 90s, CFD was being used as a standard design tool for the aerospace industry, for the automotive industry, where it's all about aerodynamics and about flow distribution, etc., over the compartments of these designs. And we see nowadays way more applications. Even, for example, complete cities are being modeled with CFD to see how the wind is flowing through the cities in terms of heat effect in cities, etc. So yeah, a lot of general opportunities in the whole industry for CFD. But of course, we will zoom in today on the water industry. So we as a business also focus, 95% of our work is really focused on the water industry. Why? Because we really believe that CFD is a very powerful tool to help scale up technologies, to have optimal designs and optimal operations of your installations. And that's why we think it's a must, and that's what we more and more see in our projects. So Wim already mentioned a lot of applications. We will talk about wastewater and about drinking water. You see it here specifically for wastewater treatment, a couple of examples of where we already worked on in the past with our CFD models. It goes from primary treatment until the anaerobic digestion part. We cannot cover all of them. We will zoom in today on all 3 of them here for the wastewater fields. So it's about secondary settlers, it's about digesters, and about a specific technology, a Demon reactor, where you will learn more about in the cases that the colleagues will present. And apart from that, also, a lot of technologies and projects that we have done in the past for drinking water treatments. Also there, starting from the source, big reservoirs, going to disinfection and the storage of finished water, let's say. So a very wide area of applications. Today, we will zoom in on the large surface water reservoirs, disinfection case, and an ozonation case. But more will come into in the next minutes. Now, let's first explain a bit CFD, what it is. It's computational fluid dynamics. So it's a science-based model based on physics, and actually even kinetic reactions can be integrated, but it's science-based. And how does it work? Actually, you start from, for example, from an existing plant or a new plant where you have a certain preliminary design. And then we draw this design into our 3D program, the software. So where are the aerators? How does the reactor look like? Where are the pumps, in and outlets, etc. So you visualize that in 3D in the model. And then we actually divide it into very small cells, 1 million or more, it depends on the case. And in each of those cells, we solve the physical equations and sometimes chemical equations. So it's transport, etc., that will be solved, all those equations that are known. And then you visualize that output. So each cell has actually a value, and you visualize that with colorful outputs. For example, in this case, you see in red a higher presence of air, in blue, low presence of air, and where there is no color, there is no air. So that's how you can visualize this complex output of more than 1 million numbers, for example. So then you have actually a virtual 3D image of your reactor, and you really understand what's going on. And then the fun thing starts. You can start playing with your design in a virtual way. So what if I draw my inlets here? What if I put the aerators there? What if I move the mixer? So a lot of scenarios can be done with that. You always see the new outputs. You can compare the outputs and come to an optimal design. So that's actually basically how it works and the typical workflow of how we implement the models. Now let's show that a little bit with an easy example. So this is a bioreactor where 2 injectors for pure oxygen are positioned at the bottom. And you want that it's optimally mixed, okay? When you do this, you actually see, you start modeling it, and you have a blue zone where actually the concentration of oxygen is very little, and red zones with very high concentrations. So it's not optimally distributed, your oxygen. And you can really see that here on this figure. And then you can start doing the what if scenarios. So a small change even, 50 centimeters of relocation, a small change in the angle, in the rotation, and you see actually that these blue spots disappeared and everything is already way better mixed. So this is, a project that took 2 weeks to finalize this project. And actually the customer could really save CapEx. No recirculation loop was needed. He could save operational costs and no additional pumping costs. And he had even a better pure oxygen transfer in a matter of weeks. So that's a very nice example of the power of such models, and I hope it also explains how it works. Now, I talked about the aerospace industry so many years ago, but we see also this trend more and more in the water industry. So CFD is becoming more and more part of, it's becoming more a business case in the water industry as well. So how did that come? On one hand, the computational speeds increased a lot over the last years. You can even have access to high performance cloud computing, etc., to run heavy simulations. And the industry, the water industry, more and more realizes also the potential of what CFD can do. And then we as a business, of course, focused a lot on tailoring our models for the water industry. And we really worked on a lot of different cases and developed tailored models for the water industry on wastewater applications, drinking water applications, specific technologies that are out on the market that needs tailoring. And then, this together with emerging needs, Wim already addressed it a little bit in the beginning. I will also zoom in a little bit more on it, but climate change, water scarcity drives the need. And then there's the digitalization trends, where CFD is also a part of. And that actually results in things we already see, that more and more utilities are actually asking CFD as a design verification already in tenders, or it's becoming way more of a standard technology already. And that's very good. I will zoom in a little bit more on the needs now. So yeah, we talked about wastewater, about drinking water, and yeah, reuse is also more and more happening. Process water, it's all interconnected more and more. And the models can really help there as well. So if you look at, yeah, what is the needs and the drivers, you have more stringent regulation, climate change is happening, more water scarcity. And this really asks for, yeah, making more optimal use of your existing infrastructure. And there, CFD can really help a lot, because if you do it better, you mix better, or you do different modifications, you can really, yeah, increase the performance of your existing plants. New plants need to be built, new technologies for new pollutants need to be built, where models can help scaling up those technologies or optimally design them, new treatment concepts, etc. So yeah, a lot of things where we think the CFD models can really help the industry tackling those challenges faster and faster. Now, that's on the challenges side, but where do we then really apply the models, in which stages? It actually goes from R&D to operations. So yeah, we've seen there were a lot of technology vendors here in the webinar. Yeah, if you're working on a new technology and you have it on a smaller scale or on a pilot scale, you need to scale it up, and you want to do that as fast as possible. Models can help there, yeah, speeding up that process, and you really know where to fine tune your technology. And then if you're an engineer working for an end user, or you're working in an end user like a utility, a drinking water utility or whatever, in the planning stage, models can really help you to virtually pilot a new treatment, for example. What will happen if I install this treatment? Their CFD models can help a lot. And then we see more than half is mainly interested in the design aspect. So yeah, detailed design, where to put the baffle, where to put inlets, mixers, so many things you can play with that have a big impact on your performance. And in the operational stage as well, yeah, how do you optimize your current plants in a way to have a smoother operation? So their models can also help a lot. All right, yeah, I talked about wastewater, drinking water, reuse, process water, and the stages. Actually, yeah, we have projects in each sector and in each stage, but we cannot cover all of them. But I think this webinar will give you a nice overview of the possibilities. And then there is a poll question, indeed. I already talked a little bit about the benefits, but I'm very curious what you think about the benefits of CFD. So where do you see the main benefits of CFD? Is it in cost saving, operational or investment costs, maximizing your assets, optimally designing it, faster and more objective decision-making, de-risking designs and building confidence, or even something else? Curious to see the results. I would vote for all of them, but yeah, all right. Mainly in the optimal redesign, which makes sense because a lot of designers are here, but also very interesting to see indeed cost saving. That's what we see in a lot of cases, that yeah, applying CFD in the design phase can also save a lot of operational costs and capex costs. I think Simon and Roberta will zoom in a little bit more. And the de-risking is, of course, also important. All right, good to see this. Then I give the floor to Roberta, who will start with the first case in Italy.
All right, thanks, Peter. So the first case example indeed brings us to Italy, in the north part of Italy, where we work with Gruppo Cap, a water and wastewater utility in the Milan region and surroundings. We help them in optimizing the disinfection, their disinfection unit. So the goal there was to ensure optimal disinfectant usage by finding the optimal dosing point, dosing location of the disinfectant, of the chemical. So this is the one that you see here on the bottom is the initial configuration of the disinfection unit, this inlet channel where the flow enters in this direction, and then there is an L-shaped configuration with a mixer before the flow splits in these two channels, channel 1 and channel 2. In their current or initial configuration, the dosing point was located here in this corner, in this purple dot. And there we wanted to see if that was an optimal location already, or we could optimize the dosing point. Then it's time for a small quiz. So we would like to ask you which lane do you think is the chemical going to take in this current configuration of the chemical point? Yeah, let's make an effort to do a CFD simulation in our mind. So is it going to be mainly in channel 1 or in channel 2, or is it going to be 50-50? Let's give it some more seconds. All right. Okay, yeah, it's the audience think that 41% of the audience thinks that 30% is going to channel 1 and 70% to channel 2. And yeah, it's an equal split because 40% also think that it's going 70% in channel 1 and 30% in channel 2. So there is a bit of division. But yeah, let's see. We'll see in the next couple of slides the answer to this question. All right, so we started with this initial configuration of the dosing point location, and then we tested many other configurations, so many other dosing points. And here on the right, you see the final improved configuration where the dosing point is placed a bit upstream in the first inlet channel. And we also included there another mixer to enhance the mixing already in the first part of the channel. So let's look at the results. So here you see the 3D representation of the chemical concentration. It's a mass fraction, so it's basically the local fraction divided by the desired fraction. So optimally, ideally, we would aim for the green, which means that the ratio is 1. As you can see in the initial configuration, despite the presence of this mixer, most of the chemical is going to channel 1, so it's almost 100% going to channel 1, and it's very little disinfectant is going to the second channel 2. With the improved situation, we can see that this is much, it's very nicely improved. So it's green in both channels, which means that the split, the chemical split between the two channels is very close to the ideal situation. So in this case, Grupo CAP could achieve several benefits from this study. So they could save up to 50% of the disinfectant dose with the improved configuration, which also led to increasing the disinfection potential by 20% in the removal of Escherichia coli. And basically, they could test virtually, so in CFD, many configuration and avoid costly and risky on-field, on-site testing. So this was a first simple case, let's say, a one-phase model, so with only liquid phase or water phase involved. But in the water industry, we know that there are many other case examples, more complex, which also involves, for example, gas or bubble raising, for example, in aeration, oxygen transfer, and so on. So here we would like to make clear that the CFD can be really tailored to any specific case study, any specific type of system, regardless of the type of design, regardless of the type of process involved, so the kinetics involved. and regardless of the type of water matrix. So basically, depending on the type of reactor, type of water matrix, and kinetics involved, we can address all of this in the CFD, going to multi-phase model, even to CFD combined with kinetics. And this is a practical example of what I just mentioned. In this slide, you see this is a bioreactor where we can visualize in time. So it's a transient simulation. We can visualize the concentration of variables like ammonia concentration, dissolved oxygen in the bioreactor, nitrate or N2O in the liquid and in the gas phase. This gives you an idea of the local concentration of your variables and also over time. So this is really the power of the CFD combined with kinetics. I cannot go into details of this slide, but we presented more in detail this case in a previous webinar on the CFD, on the application of CFD biokinetics in the water industry. So we invite you to watch the recording on our YouTube channel. All right, we can move to the second case example, and which brings us in France, in Paris. And this case is still in the drinking water domain. And in this case, we work together with Eau de Paris, water utility of Paris, in the renovation of their ozone installation for disinfection. So it's still a disinfection kind of water domain, but in this case with ozone. So it's an ozonation reactor. And they had to retrofit or renovate their ozone reaction. The goal there was really to improve the disinfection by maximizing the contact time of ozone in the water, and at the same time minimize the bromate formation risk. Also there we started with their existing design where the ozone reactor had two ozone injection chambers, initial first injection chamber, smaller one, and then a bigger one, wider second injection. And then we tested also in this case several design optimization options, and we ended up with this optimized configuration that they are currently it's currently being constructed. And what we did, we divided the ozone dose in 3 chambers. So there are 3 ozone chambers and several contact chambers. So it's a more baffled reactor. In this specific case, this is a more complex model. It's a multi-phase model where we also combined kinetics reaction, so CFD plus our Amazon model. So in this slide, you can see the 3D, the concentration of dissolved ozone in the existing design and in the optimized design, as well as the bromate formation, so the concentration of bromate along the reactor. So basically, the main conclusion there was that in the existing design, the ozone dose was not delivered optimally. So we had there was gradients of ozone, so low ozone concentration and very high ozone concentration, especially in this second chamber, very wide chamber where ozone is dosed. And in the optimized design, we could avoid this and provide ozone in a more optimal way, and which gives more uniform concentration of ozone along the reactor, while keeping the same bromate formation at the same dose. And then we could quantify the contact time of ozone along the train, along the reactor, and basically with the optimized design we could improve the contact time by 30% compared to the existing design, which also means that we can save a little bit of ozone dose. In this case, it was up to 50% less dose requirement to get the target contact time. Which means that the bromate formation can also be lowered a lot by using less ozone. All right, then I'll pass it on to Simon for the third case.
Oh, thank you, Roberta.
Right,
so
Simon. I will
yeah.
quickly come in between Simon here because we have a couple of questions coming in. And now you're here. I mean, I will ask you a question. So we have a question which is related to design. So do you, when can you start using CFD? Do you already need a certain detailed design, or can you already start in conceptual design stage?
Yeah, very good question, I think. The better the earlier, I think. Because yeah, once you have a final design, there's already a lot of work gone in that design. While yeah, it's better to at a very early stage already start looking at the design with a CFD analysis, so you can find the bottlenecks or the things that you can easily improve. You can already find them from the beginning. So that's the earlier the best, I would say.
Okay, thank you. And the second question is on the maybe for Roberta. Roberta, so there was a question on the disinfection case from COP, and then you have the disinfection case from Eau de Paris. So one is chlorine, the other one is ozone. What is the difference there? Do you have a reactive tracer kind of? Is the disinfectant reacting, or is it not reacting, or is it different in both cases?
Yeah, so that's also a relevant question. Indeed, it's a different model, let's say. In the case of Eau de Paris, so with ozone, we combine the ozonation reaction with the conventional CFD approach, where we evaluate the hydrodynamics and along with the ozone reaction. So there are reaction to model the transfer of ozone from the gas to the liquid, and then all the chemistry involved for the bromate formation and disinfection potential. In the case of the of Gruppo CAP, so the Italian case, that was the chlorine reaction can also be included, but in that case the main goal was to really observe the mixing of this chemical, which was simulated as a tracer. So in that case it says so non-reactive compound, but it could be if you really want to quantify the disinfection potential, then you should also include the reaction, and that's something that it's possible.
All right, thank you. So it really depends on the objective, huh? And
the
type of process.
Yeah.
Thank you, Roberta. All right, Simon, I will leave it to you now, so you can introduce this case.
Okay, thank you. So we will talk now about a case in the wastewater field, the deaminification process, more specifically in the US, a case from DC Water, which is a utility in Washington. If we look at the tank, so it's a deaminification tank, quite a simple tank, a squared tank with some hyperbolic mixers inside there, which you can see there. So there are 4 hyperbolic mixers, which will induce a lot of turbulence because they will mix the system. And there is also aeration underneath these mixers to make sure to have a good fine bubble aeration and distribute the bubbles everywhere in your tank. What was the problem that they were observing? They were trying to put a decanter inside this tank to have immediately a clear effluent or a cleaner effluent already from this tank. But they saw in reality that the decanter was always breaking, probably due to turbulence or something like that. They were not sure of that. So that was what we first checked in this model to see, okay, what is now the situation? And we could observe very high turbulence, as you can see, very high velocities. And we could also check the air volume fractions in this case. That had big consequences because they could not operate it continuously in that case, but they always had to slow down the mixers and then had the effluent, the clear effluent. So we were looking for other solutions. For example, what we investigated here was a baffle at the site where you have the orange pipe where you will collect the effluent. So first the water flows through this baffle at the top where the sludge can settle in between 2 baffles and then flow further where the sludge can further settle down and can enter the tank again. Of course, there is a risk that water from the bottom, due to this high mixing energy from the invent mixers, water would flow upwards. inside the baffles. So you put a small deflector, which is shown here in red, or there at the velocity vectors. But what we could see in the original design in the first try is that the flow was flowing upwards as expected, but then formed a small recirculation. And that recirculation would lead to some problems because that could have some flow through the baffle, through the hole of the baffle, and also some bubbles would go there, as we can see in the air volume fraction. Here we can see that inside the baffle, we see that the green, the small blue, shows that there is some air going into that side, which of course you don't want because you want sedimentation there, and the air bubbles would induce some turbulence. So in the end, what did we do? We tried to improve that situation by testing multiple designs, and we ended up with a smaller deflector where you try to avoid this recirculation pattern that was formed and that the flow would just flow upwards. And in the end, that was a very good case, and very little bubbles or air was now seen in the sedimentation region. In the end, DC Water really went for the building of this baffle. As you can see here, you can even see this deflector at the bottom, the gray parts there. And now it's really operating. And they really see also that no bubbles are going in there, which is a very good confirmation of our simulation. And yeah, for them, it was a big win. The project took us around like 6 weeks to complete all the simulations and to make these conclusions. So very strong case. Okay, then let's move forward to the next treatment step. We will talk about secondary settlers. We will discuss 2 cases here. One of city of Kalamazoo in the US, Michigan, and one in Sweden of Uppsala-Vatten, which is an ongoing project. City of Kalamazoo, they were planning upgrades, and they were thinking of what should we do to optimize our design. If we spend this money, how can we spend it the best way that is possible? So they came up to us with certain designs that they wanted to test. So we tested a lot of different designs that they had in mind, and also we had some brainstorms together. Can we optimize these settlers? We're talking here about circular settlers. So that's the first case. The second case were rectangular settlers in Sweden of Uppsala-Vatten, a utility. And that was a bit different. They had a problem with sludge washout during high flow. So the plant was designed for a certain flow rate, but they could see in reality that they could never achieve this flow rate, or they had sludge washout. So this problem was more focused on problem and solution investigation. So let's go to the first case, City of Kalamazoo. First of all, what we do is we really go for a model fine-tuned for this specific case. So we calibrate our settling curve based on measurements of the client, of the sludge, the real sludge properties, because that can differ from plant to plant. Once we have this, we really implement this in our unique sedimentation model, and we can have some outcomes, as you can see at the bottom, where you can see the sludge bed. So you can see the sludge concentrations inside your tank, higher concentrations in the hopper, and a stable sludge bed. This was also validated, as they had very good measurements at the City of Kalamazoo, and you can see that our model was matching very well with the data that they had. After we had this done, we went to a lot of the design cases, different types of designs that we tested. For example, the energy dissipation inlets, where we want to dissipate energy from the incoming flow. We could look at different types of baffles, for example, the density current baffle or the Crosby cylindrical baffle. And we could also change, or we played also with the real design, like the overflow weir was now not at the side. What would happen if we move this to the launder wall? These things we can all test. Some results, I will not show all the cases because we did a lot in this project. First, current design, you could see the sludge inside the tank, and in the red circle, you clearly see the impact of the incoming flow on the sludge bed. So there is a lot of disturbance of the sludge bed due to the incoming flow. So we tested different energy dissipation inlet systems to try to remove the energy and don't or have a stable sludge bed. For example, at the bottom, you can clearly see that you have now a very stable sludge bed, no impact anymore from the inlet. And that's in the end what you want. And another case of, for example, another discharge system where we were able to more efficiently remove the sludge. And in the end, that also lowered the sludge bed significantly. These are two examples. Then the last one is the other case, Uppsala Vatten in Sweden. So I will show you this slide, just one figure, because this is an ongoing project. What the problem was is that they had high flows. They saw sludge wash out. So what can you see on this figure? The streams show the lines show how the water is flowing, colored by velocity. So in the beginning, you can see the incoming pipe. The red lines are first going up and then going down. So that's the incoming flow at high velocities. So we could observe very high velocities in this first part. The other color is the sludge that you can see, and you can see in the hopper, you don't have a very high sludge concentration. So it's only like 3-4 grams per liter. So you cannot really achieve good settling there due to this high turbulence from the incoming flow. So what we're now trying to achieve is to improve this situation. And we're trying to do some scenarios with, for example, horizontal baffle, but no results yet there because that's still ongoing. And then I give the word back to Roberta.
Okay, thanks, Simon. Next case is about anaerobic digestion, still in Italy, this time with another wastewater utility, still in the north region of Italy, with Brianza Acque. So in this case, Brianza Acque wanted to upgrade or replace the current sludge mixing system in their anaerobic digester because it was outdated and an old fashioned system, let's say. And the goal here was to improve the sludge mixing for optimal biogas production. So the current design, System 1, their current sludge mixing system, it was made of 4 sludge recirculation pipe that you see on the top of the digester, where the sludge is being recycled from the bottom back to the top of the digester, and 6 gas lances for the recycle of the biogas to enhance the mixing in the bottom part as well. So there we first started with the current design, System 1, and we tested also other design or mixing technologies, and here we are presenting the new design, the new mixing system they decided to go for, and this new design, System 2, in this case they replaced this sludge recirculation pipe and the gas lance with 4 sludge recirculation pipe at the site, recycling sludge at different heights and in different angles, different orientations, with nozzles injection. So there we started with the more conventional CFD hydrodynamic study, where we could analyze and understand the flow pattern in the digester. Here you can see now an animation of a plane from the bottom of the digester moving up to the top of the digester. and the velocity magnitude are being shown here. So you can see that with system 1, so with the current system, very low velocity, very low mixing of the sludge occurs at the bottom. So you see that velocities are almost 0, so in blue. And while with the system 2, so with the new system for the sludge mixing, velocities are much higher thanks to this nozzle, which can really increase the movement, the mixing of the sludge already at the bottom. And as the plane go high, we can see that the velocity decreases in system 2, and again they go up in the top part where the sludge is being recycled also from the top. While in system 1 we can see that there is a bit more turbulence at the top due to the presence of these gas lands, which is recycling the biogas, leading to more turbulence, but only in the top region. So next to this conventional CFD hydrodynamic study, what we also did, we included the behavior of the solids, so the suspended solids concentration, to have an evaluation of the long-term operation of these two systems. And in system 1, you can see that in the long term, a thick layer of highly concentrated solids is being formed at the bottom due to the very bad mixing in the bottom. And this is what also Brianzacque could suspect it was happening in their digester. And there we proved that their feeling was actually correct, and there was a thick sludge layer in the bottom of their digester. In system 2, this can be minimized thanks to this better and enhanced mixing due to the nozzles injection. And finally, we could quantify the improvement by looking at the suspended solid distribution in this bottom part of the digester that is more difficult to mix because of the tendency of the solids to accumulate at the bottom. So in system 1, so the current system, you can see that there is a huge variability of the suspended solid concentration in this bottom layer, from very low or low concentration to very high concentration. While in system 2, the orange line, this is much more improved, and you can see the curve is very steep, is almost vertical, which means that the concentration is very uniform. And in this case, Brianzacque could really save a lot of time in testing and in deciding which technology they should go for. So having a more efficient design in the end, and also de-risking of the design by having the possibility and the flexibility to test different configuration of solid mixing system. And finally, also a reduction of the cost that normally comes along with more efficient and better designs. All right, and then I'll pass it on to Simon again for the last case.
Okay, thank you. So we will talk now about big drinking water basins. So we go a bit to a different scale. The previous examples were all about relatively small reactors compared to big water basins. We're talking now around in a range of like hundreds and more than 100 meters. So it's a bit a different scale. This one is a basin of Evides in the Netherlands. It's a basin that's for drinking water and softening. So they add some particles there to soften the water. And what they see in reality is that particles when they are dosing these particles, it's like once a day, they see a lot of short circuiting. After a few hours, 2 hours, they see a lot of short circuiting already at their outlet. And these particles can cause some problems later onwards in the treatment process of the drinking water. So that's, of course, what they want to avoid. So how do we do this? We start from the real basin, the real geometry, the real bathymetry. as you can see in the middle, the real depth of the basin. And then we build this in our own software. We also include some aerators, as typically these basins are sometimes also aerated, not always, or it's not always on. In summer, typically it's on, in winter it's off. So that can really change how the flow goes. And that's something that we can investigate. So in the current situation, what do we see in the flow pattern? You can see that from the inlets, the water just flows straight to the other side of the basin and flows to the outlets. So that's the short circuiting that we could really observe very clearly in our simulations. So what do we want to do? We try to remove the short circuiting. For example, what we try to do is put a baffle in front of the inlet and see how this impacts the flow. If we go to these scenarios, we can see that the flow pattern changed completely. So we had more flow along the sides of the basin, which would make the path that the particles would take to the outlets a bit longer, which would be beneficial for the softening process. If we look at the right, we see the aeration. So there we see slightly higher velocities, especially in the middle, to remove these dead zones. So that's also one of the options that they always put on the aeration when they dose these particles. Of course, only from velocity vectors, it's a bit difficult to really conclude something. So we also typically run the mean water age, which gives you an idea of how old the water is at each location in your basin. For example, you can clearly see the short circuiting at the younger water that flows just from the inlet and part flows to the outlets. In our new simulation with the scenario, we had this big dead zone in the middle. And when the aeration is on, we have a very uniform mean age in the basin. Only at the side you can see the incoming flow still visible. If we include here also particles, so we also did some particle tracking, and we could investigate how long it takes from the inlets before they get to the outlets. And that gave us very interesting results. For example, in the current situation, we could clearly see that after 1-2 hours, few hours, we could already see that they are appearing at the outlet. And that's the real short circuiting that they were also observing. While with our scenario, so with this baffle, it gives us a few extra hours before we could monitor these particles at the outlets. And also with aeration, that's the case due to the extra mixing that we do there. So that could really give them the opportunity to grow the particles and to also settle them in the basin itself. So that's a very practical way of how we can use CFD. As a final case, I also would like to show this one. So this is a basin of also in the Netherlands of PWN. You see here, it's also a softening process where they put particles, and it's the white colors that you see here. And we had a very good match with our CFD because it was visually very clear. So this is our CFD simulation, and we could see we had almost a perfect overlap, and we could also really visualize the short circuiting here. So then that were all the cases. Then I give the word back to Wim.
Right, thank you, Simon and Roberta, for presenting those cases. This brings us to the closing remarks and the conclusion of this webinar. So we have 2 more slides for you, but we also have some remaining time for Q&A at the end. Okay, so please stay for the discussion if you still have some time. All right, so let's start with some closing remarks. We are in this business now for quite a while. Even before we launched this business, we were working on CFD a lot. And after all these years, we can say that, we could help removing a couple of these worries around CFD in the water industry, leading to accelerated adoption, leading to broader exposure or implementation in the water industry, which is very good news. Some of these very important topics are these ones on the slide here. These are the practical items that are extremely important for practitioners. For example, how long does it take? Not only how long does a simulation take, but if we integrate CFD into our project, What is the duration? Well, all we can say is that based on these over 150 cases we have done, it's probably close to 200 at this moment, that CFD really accelerates design projects. And it already also facilitates collaboration between teams. So we are more and more a part of a very big team of different parties like the tech vendor, end users, engineering firms. We work closely together, and these things really facilitate and accelerate the decision making. Never before, never in a single project, simulations were the time limiting factor. So this is also something we want to remove. You know, CFD takes long, and well, 20 years ago, a CFD simulation was taking long. Today, simulations never ever are the time limiting factor or the hindering factor in a project. Data needs are also very limited because it's physics-based models and because we have tailored models for the water industry that were validated a lot in the past. So this also brings us to the reliability and accuracy. In 80% of the cases, we do not need any validation. And often it is not possible because we are working on a design project where you don't have an existing facility, you don't have data yet. So we rely on the very solid foundation of physics and the tailoring of our models that have actually been applied at numerous cases. And the value is clear. The value is very clear to many of those stakeholders, not only the end user, because we should remember that infrastructure probably needs to survive, needs to be operational for 20, 25 years. So it's really, you have really a lot of value if you do a proper design. But it's more than just some velocities or mixing. We are reducing greenhouse gas emissions. This is a topic especially very important in the last 3 years. We are improving the efficiency of the process. So this means chemical and energy saving. And we are also, of course, improving the process performance when it comes to effluent quality or really the treatments. So this is really multi-benefits. We have few projects where we are enhancing only one of those objectives. So this brings us to the conclusions of this webinar. We hope that we could show you a wide array of applications. We have way more to show, but we can't. But of course, you can always reach out to us. There are very few unit operations we have not been working on. It's almost every physical, chemical, or biological technology, even electrochemical technology we have been working on. So yeah, the applications are really wide. And the business case is very important for those three stakeholders on the slide, the technology vendors, which have a lot of commercial benefits and a lot of time competitive benefits. When we work with engineering firms and consultants that don't have this in-depth expertise in CFD, well, there's a lot of de-risking, a lot of stress relief. There is better and faster decision-making in design projects. So this is really very interesting collaborations. And when we work with the end users, of course, they have to operate those assets. And we focus on these 3 E's. I already mentioned them: effluent, efficiency, emissions, so cost saving and environmental and business benefits, or CAPEX, OPEX in design stage, in retrofit stage, in redesign stage, in operational stage. And what is a very important aspect right now is, in view of the new regulation, in view of adaptation for climate change, in view of mitigation of emissions for net zero, in view of making the shifts towards reuse, well, you have to use your existing assets in a different manner. And before doing a very expensive upgrades, you have really a lot of value in maximizing the use of the existing assets. And we literally could postpone upgrades with 5 to 10 years in certain circumstances. And this is about a lot of money. So before you leave and we go to the final Q&A, feel free to visit our website or subscribe on our LinkedIn channel, because we do a lot of webinars, new webinars. You will see the invites appearing, but we also do LinkedIn live case webinars where we pick a specific one case, and together with a customer, we dig into that case specifically. So it's really more topical, these things. So just follow us on social media and you will for sure get these invites. So before we go to the final Q&A, for the people that really need to leave, we really thank you. It was really a pleasure having you in our webinar, and many of you have attended several of our webinars. And this means a lot to us. And also for the new people here, feel free to come back and reach out to us. It really means a lot to us, you attending and asking all of these interesting questions. And for the people that need to leave, thank you very much for attending. And people that wants to stay, of course, a little bit longer, we still have a remaining Q&A. So let's look at the residual questions. Maybe Peter, can you come up? We have a digital twin question.
Yes, here I am.
You quickly referred to in the beginning somewhere, you made the link with digital twins. Digital twins is at the operational stage. It is real time. CFD is seen in the design stage. It is offline. How do you make the connection? Where do you see the connection between digital twins and CFD? Yeah, interesting.
Very good question. Well, digital twins really mainly focus actually on the kinetics, on reactions happening. And what you see there is in digital twin or the kinetic models, typically you can use a certain approach where you assume that your whole reactor is completely mixed. But in reality, we see from the CFD that is not really happening. We see that there are a lot of gradients. So actually, to have a real good predictable digital twin, in many occasions, for example, for N2O predictions or effluent predictions, we start first with a CFD simulation. And based on the insights of how everything is mixed, we bring that mixing knowledge into our digital twin model, which is a kinetic model. And we divide our reactor in different compartments and then make more realistic predictions. So we bring more accuracy from the insights from the CFD into our dynamic kinetic models. And then they are more robust and reliable.
All right, thanks, Peter. So yeah, it comes down to the fact, we often explain it as having the physics right in order to avoid having to calibrate biokinetic or chemical parameters to compensate for missing physics. Right. So that's separating these two. Okay, we have a question for Simon now on the settlers. Simon, you have actually answered this question partially, but I would like to come back to it. How do we ensure that settlers are reaching let's say stable conditions? How can we conclude like, okay, let's stop the simulation, this is the end result?
Yeah, that's a very good question indeed, because settling is a slow process. It takes hours before you have a real stable condition. And in our simulation, we also run our settling model transiently. So it means that we really run the hours that are needed, and we monitor just the sludge bed height, the amount of sludge in the tank, and we make sure that all these parameters get stable before we go to the post-processing and the final results.
All right. Okay. And then a related question to a process where you have solids, for example, MBBRs, moving bed biofilm reactors, where you have these plastic carriers flying around in a reactor. We didn't show cases on this. Can you elaborate a little bit on that? Can we model this, and what can we do typically in these cases?
Yes, of course. So yeah, on top of what we have shown here, you can also add particles. Yeah, the density of the particles, the size of the particles, how the particles look like. So all these things you can mimic in a CFD simulation, and you can integrate these particles. You can look at the interaction between the water and the particles. So definitely, we also had multiple cases of this, of an MBBR, for example, in our company. So yeah, that's definitely possible, and we can definitely look at that, how the distribution of the particles would be, of the media, or all these types of things.
All right, good. Well, thank you. So if I can conclude this, we have no limitations on things we can simulate and model. We haven't seen a lot. So well, I think with this, we have reached the end of the webinar. It's 5 p.m. in Belgium or Central Europe. And again, for the people still here, which are still quite a lot, thank you very much for staying until the very end and for joining our webinar. And we really hope to see you again and interact with you in the future. Thanks so much.